Hello students, welcome back to the 10th video of this playlist. In this video, we will discuss the last question from the most recent past paper of Physics Unit 2, which is the October 2024 paper. So let's see what's the last question. That is the question number 19 of this paper. Okay, so here is the question number 19. So let's get started with question number 19. A photomultiplier is a device that can detect very low intensity light. Okay. In a photomultiplier, a metal plate called a photocathode is connected to the negative terminal of a power supply. Electromagnetic radiation incident on the photocathode can cause the photoelectric effect. Okay. So part A here is asking to describe the photoelectric effect. Okay, so we have to describe the photoelectric effect. Okay, so we know that in photoelectric effect, basically when an electromagnetic radiation is incident on the metal plate, okay, then the electron from the metal atom, it it interacts with with a photon from the EM radiation and absorbs energy from it and gains energy basically. So as it gains energy greater than the work function of the metal plate, then it gets emitted. This is the photoelectric effect, isn't it? So that's what we will explain here. An electron interacts with a photon as EM radiation is incident on the uh, metal plate. Okay, as the electron gains energy greater than work function of the metal. So the electron get emitted. This is the photoelectric effect. Emitted. That's it. This is the photoelectric effect. Fine. Okay. Next is part B. In part B, the question says the photomultiplier can only detect electromagnetic radiation that causes the photoelectric effect. So the question B is asking to explain why the photomultiplier cannot detect some frequencies of electromagnetic radiation. Okay, so the photomultiplier, it can detect only the EM radiation that can cause the photoelectric effect. So we know that for photoelectric effect to happen, there is a minimum energy that the electron should gain, right? This is basically the work function amount of energy. So all EM radiation, their photon energy is not greater than the work function of the metal plate, right? So that's why all EM radiation cannot make this photoelectric effect happen. Okay, so for 2 marks, what we will write here is that first we will say that uh, to cause photoelectric effect, to cause the photoelectric effect, electron, to cause the photoelectric effect, electron must gain energy greater than the greater than the work function of the metal, right? Gain energy greater than the work function of the metal. Okay, so we know that the the photon energy is proportional to the frequency, right? So that means the frequencies, all the frequencies of electromagnetic radiation is not above the threshold frequency, right? So since the question is asking why the photon multiplier cannot detect, so we will say as photon energy is proportional as photon energy is proportional to the frequency of EM radiation, or electromagnetic radiation, so the photomultiplier cannot detect the EM radiation, the electromagnetic radiation that has frequency less than the minimum frequency. Okay, minimum frequency, we can say that as threshold frequency. Okay, that's basically the threshold frequency. That's it. These are the 2 points we can say for the explanation why the photomultiplier cannot detect some frequencies of electromagnetic radiation. Fine. Okay, next is part C. So in part C, the question says visible light has range of wavelengths from 380 nanometer to 700 nanometer. The work function of the material used to make the photocathode is 1.48 electron volt. So the question is asking to deduce whether the photomultiplier can detect all wavelengths of visible light. Okay, so the work function is given, so we need to consider the maximum possible photon energy from this visible light, okay, and the minimum possible uh, photon energy of the photons of visible light. Okay, so we know that the energy of photon, it is equals to hc over lambda, right? So that means the photon energy will be maximum. Okay, we need to consider the minimum photon energy only, because uh, we have to consider, if you see the maximum wavelength, the maximum wavelength will give the minimum photon energy. So if you just find out the minimum photon energy, that's enough to make this deduction. Okay, so minimum photon energy of visible light can be found from maximum wavelength, right? Because photon energy, it is inversely proportional to the wavelength. Okay, so consider the minimum photon energy. So E equals to Hc. The value for H, it is given in the formula booklet. It is basically uh, 6.63 times 10 inverse 34. So 6.63 times 10 inverse 34. So 6.63 times 10 inverse 34, okay, times 3 into 10 to the power 8, the speed of light in vacuum, over the lambda. Lambda is 700 nanometer. So 700 times 10 inverse 9. That much joule of energy. Okay, so let's calculate it out. So 6.63 times 10 inverse 34 times 3 into 10 to the power 8 divided by 700 times 10 to the power negative 9. So that would give you 2.841428571 times 10 inverse 19 joule. Okay, so in electron volt, it is basically we have to divide this energy. So divide this energy 2.841 dot 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 times 10 inverse 19. Divide this energy by the charge of an electron, that is 1.6 times 10 inverse 19. Okay, that much electron volt. Okay, so if you convert to electron volt, you will get 1.6 times 10 inverse 19. So that would give you 1989 over 1120, that is basically 1.7758928857, that much electron volt, which is less than the, okay, which is basically greater than, not less than, 1.48 eV. Okay, which is greater than 1.48 electron volt. So the minimum possible photon energy, this is greater than 1.48 electron volt, the work function of the material. That means the photomultiplier can detect all wavelengths of visible light. Hence, the photomultiplier can detect all wavelengths of visible light. That's it. That's the deduction we can make out of here. Fine. Okay, next is part D from question number 19. Okay, here the question says, in the photomultiplier, the photocathode and several other metal plates are in a vacuum as shown. Okay, we can see in the figure. Okay, an electron is emitted from the photocathode with a speed of 1.35 times 10 to the power 6 meter per second. There is a potential difference of 108 volt between the photocathode and the first metal plate. Okay, the PD, the potential difference between the photocathode and the first metal plate, it is 108 volt. This PD causes the kinetic energy of the electron to increase. Okay, fine. So the part D is asking to calculate the kinetic energy in joules of the electron at the instant it collides with the first metal plate. Okay. So the kinetic energy gained, okay, the kinetic energy of the electron we have to find out as it hits the metal plate, the first metal plate. So we know that the electron, since the electron will be accelerated by the potential difference, by this potential difference, so definitely the energy gained by the electron will gain the energy that has been work done by this potential. Okay, so work done by an electrical potential is W equals to VQ. Okay, so del E, the gained energy, this is VQ. So V is the PD, that is 108 volt, times the charge of an electron, that is 1.6 times 10 inverse 19, that much joule. Okay, so now calculate VQ. 108 times 1.6 times 10 inverse 19, so that would give you 1.728 times 10 inverse 19 joule. That much energy will be gained. But the question is asking the total amount of energy at the instant it collides with the first metal plate. So energy of electron, it would be the initial amount of energy, it was 1.3. Okay, it's not given, so we have to find out here. So half mv square, mass of an electron, it is 9.110 times 10 inverse 31 kg. So half mv square, right? This is the kinetic energy. So v speed is given as 1.35 times 10 to the power 6. So 1.35 times 10 to the power 6 whole square. That much energy. This is the initial kinetic energy plus the gained energy, that is 1.728 times 10 inverse 19, that much joule. Okay, now just calculate the value. Okay, so half times 9.110 times 10 to the power negative 31 times v squared. V squared is 1.35 times 10 to the power 6 whole squared. So this is basically 8.3014875 times 10 inverse 19 joule plus 1.728 times 10 inverse 19. Okay, I have wrote 10 to the power 19, 10 inverse 19. Okay, so the total energy you will get, it is 1.01. Okay, it is 1.0029. Okay, that would give you 1.002. Okay, wait, it is basically not 1.001, it is 1.811014.875 times 10 inverse 17, that much joule. Okay, I calculated it wrong earlier. So the correct uh, total energy, it is 1.81. After three significant figures, we can write 1.81 times 10 inverse 17 joule. Fine. That's the answer for part D. Fine. Okay. Next is part E, the last part of question number 19. So here the question says the electrical circuit shown includes four resistors A, B, C, and D, which apply a PD between adjacent metal plates. Okay. So there are two resistors A, B, C, D. They apply the PD between the adjacent metal plates. Okay. Each resistor has a resistance of 85 kilo ohm. Okay. They have a resistance of 85 kilo ohm. When the switch is open, that means when the circuit is incomplete, the PD across the power supply is 1960 volt. That is the EMF. EMF of the source, it is 1960 volt. When the switch is closed, the PD across resistor A is 108 volt. Okay, it is 108 volt. Calculate the internal resistance of the power supply. Okay, so we need to find out the internal resistance of the power supply. Okay, so the resistance of the each resistors, it is given there. It is 85 kilowatt. Okay, kilo ohm. Okay, so we know the resistance R, we know the PD across the first resistor. From there we can find out the we can find out the current to the circuit, right? Okay, so there are four resistors with the same resistance A, B, C, D. So since the resistance is constant and they are connected in series, therefore current through all of the four resistors will be equal. So the total power supply, it is 1960 volt. Therefore the PD across the resistor A, it is 108 volt. Okay, so that means the PD across the other resistors will be also the same, right? Because we know that V equals to IR. So here R is constant, so PD. We need to figure out the PD. R is constant, current is also constant. So V is basically constant. So 108 times how many resistors? 4 resistors. So total PD we got here, it is 432. Okay, this is the total PD. This is the base. This is basically the effective PD. Okay, and therefore the lost PD, we have to figure out the lost PD. Okay, let me show you the workings. Uh, Effective PD, it is called the terminal PD. V terminal. V terminal, this is equals to 108 times 4 volt, that is 432 volt. So lost PD, that is V lost, it is equals to V lost, it is 1960 minus 432, that much volt. So that is basically 1960 minus 432. This is 1528 volt. This is the lost PD. Okay, so we got the lost PD. Now we know the PD across the resistor A. We know the resistance of the resistor A. So we can find out the current through it. V equals to IR, right? So I equals to V over R. V is 108 over the resistance. This is 85 kilo ohm. So 85 times 1000, that much ampere. So that would give you 108 over 85,000. So this is basically 27 over 21250, that much ampere. Okay, now we got the lost PD. So lost PD, it can be written as V lost equals to current through the circuit times the internal resistance. So we need the internal resistance. So V lost, it is 1528 over the current, which is 27 over 21250, that much ampere. So the unit for resistance, it is ohm. So let's find out the value. So 1528 over 27 over 21250. So that would give you, that's a very large number, 1202592.593, that much ohm. So we can write this, it is basically uh, okay, 12 lakh 2592, right? So we can convert it to three significant figures. So if you consider three significant figures, it would be 12 lakh. Okay, 12 lakh ohm. Okay, so 12 lakhs can be written as 1 2 3 4 5 6, right? So 1.2 times 10 to the power 6, or 10 to the power 6 ohm, or you can say like this, 1.2 mega ohm. That would also work, because 10 to the power 6 in standard form it is 10 to the power 6. In prefix you can use mega ohm. Okay, so we got the resistance, internal resistance of the power supply, it is 1.2 mega ohm. And that's the end of the most recent past paper of physics unit 2, which is the October 2024 paper. Fine.